A team of Japanese radio astronomers using a giant radio telescope in Chile has found a startling array of molecules in star-forming regions of a galaxy 18 million kilometers away. In a paper published this week in the Astrophysical Journal, graduate student Ryo Ando from the University of Tokyo and colleagues turned a sprawling collection of radio telescopes called the Atacama Large Millimeter Array ALMA on a galaxy known as NGC 253, also dubbed the Sculptor Galaxy, and the Silver Dollar Galaxy, in an effort to examine its star-forming regions in unprecedented detail. The researchers chose the ALMA instrument for their work because its 66 radio telescopes are laid out in a network that can be rearranged as needed in order to allow them to zoom in on regions of interest. They also stand on a high, dry Andean plateau, 5,000 meters above sea level, high enough to be above nearly half of the Earth's atmosphere. That allows them to zoom in on NGC 253 so tightly that they can resolve regions as small as 30 light-years across. NGC 253 was chosen as the target of the study because it is a starburst galaxy, meaning that it is currently an active star-forming or baby boom galaxy. That makes it of interest to astronomers wanting to understand both star-forming processes and the manner in which galaxies evolve. The first thing that the astronomers found was a collection of 8 giant gas and dust clouds in which stars appear to be forming. But the astronomers were able to do more than just map these phenomena. They also found spectral signatures that could be used to identify the molecules contained in these gases cocooning the infant suns. In some of the clouds, the mix of gases was fairly simple. But they weren't identical, even when they were only a few light-years apart. And one contained a surprise. The crowded molecular emission lines filling the spectra were like trees in a dense forest, Ando says. That one cloud, he and his colleagues found, proved to have the footprints of 19 different molecules, ranging from simple ones such as hydrogen cyanide HCN to more complex ones such as methanol CH3OH, propylene CH3CCH, thioformaldehyde H2CS, and acetic acid CH3COOH. The reasons for the differences are not yet well understood, Ando says, but there are a number of hypotheses. One possibility is temperature, he says. In fact, the molecular forest is outstandingly warm, about 90 degrees Kelvin minus 180 degrees Celsius, while typical molecular clouds take much lower temperatures, 10 degrees Kelvin or minus 260 degrees Celsius. It is possible that the hot environment is closely related to rich chemical composition. Another possibility, he says, is that the clouds are at different stages in their evolution. Thus, the molecular forest cloud may be the youngest. We suspect that it is an aggregate of dense and warm molecular gas cocoons around baby stars, he says. Similar gas clouds can be found in our own Milky Way galaxy, Ando says, but this is the first time scientists have had a chance to compare them to those elsewhere. This will not only make us understand other galaxies, but will help us know the detailed nature of our own galaxy, Ando says. Mark Krumholz, an astrophysicist specializing in star formation at Australian National University, ISNT, surprised about the diversity among the star-forming regions seen by the new study. Stars form in complicated clumpy regions, so it is not uncommon to find several clumps near one another at different stages of the evolutionary scheme, he says. What's different from own galaxy, he says, is the size of NGC 253's star-forming clumps. In our galaxy, they are on the order of a couple of light-years across, containing between a few hundred and a couple thousand times the mass of the Sun. The things reported in this paper are a factor of about 10 larger and a factor of about 100 more massive, he says. Even more interesting, he says, is the discovery that NGC 253's clouds have coherent chemical signatures across their much larger star-forming clumps. If you took something like a Milky Way star-forming region and put it at the distance of NGC 253, Krumholz says, it wouldn't look like this. There would be regions with different chemical signatures, but they would be small enough that when you blurred the image to 30 light-year resolution, those variations would average out. In NGC 253, however, that's not happening. That suggests that star formation in these clumps is somewhat synchronized, with an entire clump turning on at once, he says. And this, in turn, suggests that whatever is happening in NGC 253 is governed by some type of galaxy-wide process, rather than the smaller-scale processes we currently see in our own galaxy. Though, what, exactly, that process might be remains to be discovered. Ando adds that this is part of what makes science cool. New technologies make it possible to unveil hidden aspects of familiar things, he says. This gives us another mystery, which again drives scientists.